Welcome to this explainer. Today we are going to completely unpack exactly how to master RAM and ROM for your Cambridge Computer Science exams. And we're doing it by looking directly at the principal examiner reports. We're talking specifically about syllabus codes like 9618, but these strategies absolutely apply whether you're tackling 0417, 0478, 0983, 0984, or 2210. So we're going to be using a strategy today that I absolutely love. I call it the jazz musician. Think about it for a second. A legendary jazz musician has to know all the fundamental scales, the chord progressions, and the absolute strict rules of music perfectly before they can ever step on a stage and improvise a masterpiece. That is exactly what you need to do to conquer these rigorous Cambridge exams. You have to improvise within a very strict structure. You have to know the rules cold before you can break them creatively to solve complex scenarios. To set the stage here, I want you to imagine a classic, high-stakes past paper scenario. Let's say we're looking at a notoriously tricky question from a paper like 9713. The question asks you to evaluate the exact memory requirements for an automated robotic manufacturing system. Now, I want to introduce you to two archetypical students that we literally see called out in the examiner reports every single year. Let's call them Alex and Sam. First, we have Alex. Alex is what I call the knowledge dumper. Alex sees the words RAM and ROM and just overloads the exam paper with raw computer science facts. Alex writes down that random access memory is volatile, read-only memory is non-volatile, explains what they stand for, and fills a whole page. But guess what? Alex completely fails to offer any actual analysis applied to the robotic arm. Zero application. Then, on the flip side, we have Sam. Sam is a rusher. Sam skims the scenario, totally misses the specific command word requirements, and just writes a quick generic answer that completely ignores the extreme context of a highly volatile manufacturing environment. And the result? You look at their papers and they are just covered in red pen marks. Both of them lose massive marks, despite actually knowing the technical material. So how do we fix this? How do we turn those red marks into green checks? Let's find out.
Okay, our agenda for today is packed. We're moving through 5 crucial sections: core principles of memory, the method mark strategy, the deconstruct, solve, evaluate framework, 3 crucial examiner warnings, and finally, acing comparative analysis. Let's dive right in.
Section 1. Core Principles of Memory. Moving beyond rote memorization. Right off the bat, Cambridge examiners emphasize over and over again that rote memorization simply isn't enough anymore. Remember our student Alex? Alex relied entirely on reciting textbook definitions. But here's the reality check. The Cambridge exams are not vocabulary tests. They are rigorous tests of applied logic. This is where our jazz musician strategy becomes absolutely vital. The examiners explicitly state in the principal examiner reports that top-performing candidates, the ones securing those top grade boundaries, exhibit a connected conceptual understanding that is fully transferable to entirely unfamiliar contexts. What does that actually mean for you? It means if the exam suddenly asks you about the RAM and ROM requirements of a smart refrigerator, an autonomous military drone, or a critical medical life support system, you can't just write down your generic definitions. You have to look at that completely unfamiliar context and improvise your application of the facts on the spot. For example, if you get the autonomous drone scenario, you need to instantly identify that the drone desperately needs ROM for its fundamental hard-coded flight stabilization algorithms. Why? Because those instructions absolutely cannot be lost or corrupted when the system is powered down, or if there's a temporary power fluctuation. But at the exact same time, it needs incredibly high-speed RAM to process real-time environmental data streaming in from its optical sensors and gyroscopes. If you can explain how those two memory types interact to keep that specific drone in the air, you are showing transferable understanding. That is what gets the marks. Examiners explicitly note that students who reference cross-topic connections across these cognitive domains achieve significantly higher marks. You see, Cambridge Computer Science specific assessment objectives target very distinct cognitive domains. We're talking about knowledge and understanding, application, and analysis. But how do you actually show the examiner you've mastered all 3? To bridge these domains, the absolute top students use what we call the PEAL framework. That stands for point, evidence, explanation, link. So when you make a point about RAM, you don't just stop there. You provide evidence directly from the scenario they gave you. Then you explain the technical mechanism of how it works. And finally, and this is the crucial part, you link it back to the system's overall performance. Listen, if you're discussing memory, do not isolate it in a bubble. Connect RAM performance to the processor's clock speed. Connect ROM limitations to the security of the embedded system. By weaving these topics together using the PEAL structure, you're flashing a massive signal to the examiner that you truly understand the entire computing ecosystem. Now, before we continue and break down the rest of these command words and really get into the weeds, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving on to Section 2, the method mark strategy, rewarding the process. This right here is where we start seeing the massive transformation for students like Alex and Sam. This is where we stop obsessing solely over the final conclusion and start focusing heavily on the journey. This is how you trade those harsh red pen marks for beautiful green check marks. You have to understand that the examiners actually want to see your brain working on the page. Showing your work, whether you are extracting from complex binary representations or calculating huge blocks of data, is just as important as getting the correct conclusion. I see so many students completely panic during an exam if they realize they don't know the exact final answer or if they hit a wall with the math. But the method mark strategy is your ultimate safety net. Imagine an exam question asks you to calculate the required RAM capacity for a specific bitmap image cache. It's a huge, multi-step calculation. What happens if you accidentally mess up the final arithmetic because you're stressed? In a lot of subjects, you get a 0. But in computer science, if you use the method mark strategy, you can still get the vast majority of the marks. How? By showing every single step of the process. You clearly show the examiner that you extracted the color depth. You write out the calculation for the total number of pixels. You explicitly show the conversion step from bits to bytes and then bytes to kilobytes. In computer science, data interpretation skills are absolutely critical. You have to document your evidence-based reasoning every step of the way, making it impossible for the examiner not to give you points. To do this effectively, you must apply algorithmic thinking to RAM and ROM problems. You do this by following this exact procedural framework to absolutely guarantee your method marks. Think of this as your internal pacing mechanism. If our rushing student, Sam, had just paused and followed this procedural framework, they wouldn't have missed those crucial command words. Instead of just hastily writing ROM is used for the boot program, you need to apply algorithmic decomposition. Step 1, break down the system requirements. Step 2, select the appropriate memory structure for those specific requirements. Step 3, explain the implementation. Step 4, evaluate it. I really want to stress this. Algorithmic thinking isn't just for your programming or pseudocode questions. It is a highly structured way of thinking that you must apply to hardware and theory questions too. When you deconstruct a hardware scenario with the exact same rigor that you would use to write a Python script, you literally, mathematically guarantee your method marks. Okay, I need your attention right here. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's jump into Section 3, Deconstruct, Solve, and Evaluate, the problem-solving framework. I like to treat this section as an interactive workshop. Whenever you face a complex RAM or ROM scenario, maybe they give you a massive data table of memory access times or a highly detailed system specification, I want you to force your answer through these 5 sequential steps to evaluate alternatives and justify your approaches. This is the Deconstruct, Solve, and Evaluate framework, and it's a lifesaver. Let's do a quick data scan challenge. Imagine a scenario where you have to design the memory architecture for a next-generation smartwatch. Step 1, identify given information. You highlight the constraints in the text. It's a wearable, so it has low power limits, physical size constraints, and needs an embedded OS. Step 2, break it into logical steps. What does the watch need to boot up? What does it need to track your heart rate dynamically during a run? Step 3, solve systematically. You allocate the low-power ROM for the critical firmware and the fast, efficient RAM for the dynamic user health data. Step 4, check for reasonableness. This is huge. If your logical breakdown somehow suggests that this tiny digital watch needs 16 gigabytes of standard desktop RAM, you need to pause, look at your work, and check your reasonableness. That physically doesn't make sense. Step 5, make justified recommendations. This is where you hit those highest assessment objectives. You don't just say, use RAM. You evaluate alternatives. You compare approaches. You tell the examiner, while standard DRAM could work theoretically, the specific real-time constraints and power limits of this wearable smartwatch justify the use of specialized SRAM for the cache, despite the higher cost, because of its superior access speed and lower power draw. Boom, that is how you secure top marks. Section 4, 3 crucial examiner warnings straight from the principal examiner reports.
According to the hard data pulled from thousands of exam scripts, there are exactly 3 major pitfalls that trap candidates every single year. When facing a complex data table showing memory access times or a really dense multi-part hybrid system question, students just freeze up and panic under the pressure. Let's pull back the curtain and reveal exactly what these 3 traps are, so you can extract the core trends without losing your footing.
Here's the truth. If you use an algorithm out of context or forget your edge cases, your conceptual knowledge of memory won't save your grade. Let's treat this like a find the flaw challenge. Let's look at warning number 1, using the wrong application for the context. Listen to this flawed sample paragraph from a past exam. A student wrote, "The automated greenhouse system will use ROM to store the daily temperature readings so they are not lost, and RAM to store the operating system." Did you catch the flaw? You absolutely cannot write daily fluctuating temperature readings to ROM during runtime because ROM is by definition read-only. And storing the base OS entirely in volatile RAM without a non-volatile backup means the entire greenhouse dies the second there's a reboot. Complete disaster. Warning number 2 is forgetting boundary conditions and edge cases. When you are evaluating memory for a system, you have to ask the extreme questions. What happens when the RAM is completely full? Have you discussed virtual memory paging? Have you considered the critical edge case of a sudden power interruption? Top students always address the extremes. And warning number 3 brings us to the most critical error of all.
This quote right here is the ultimate examiner alert. The examiners are literally telling you, no matter how accurately you define RAM or ROM, a generic answer will fundamentally fail to secure top marks. This is exactly where our student Alex lost all their points at the beginning of our explainer. Alex wrote a perfect textbook definition, but a generic answer is a weak answer. Every single point you make must inextricably link to the given scenario. Let's do a 30-second speed writing challenge in our heads. To avoid the generic trap, your answer should look like this perfectly structured Peel paragraph evaluating a car's engine management system. Point: the system requires non-volatile memory. Evidence: the engine timing parameters must be reliably retained even when the vehicle's ignition is completely turned off. Explanation: ROM is utilized to store these hard-coded instructions permanently on the chip. Link: therefore, utilizing ROM ensures the vehicle can safely and reliably start up every single time without requiring the parameters to be reprogrammed by a mechanic. Do you see the difference? That is incredibly specific, heavily contextualized, and that is exactly what the examiner is looking for to award maximum points.
Let's bring it home with Section 5, Acing Comparative Analysis, Embracing the Dual Perspective. Listen closely. You cannot just list the differences. True high-level critical analysis demands that you also identify exactly how these memory types are fundamentally similar. Too many students fall into the trap of creating a simple elementary T-chart. On the left side, they write RAM, volatile, read/write, temporary. On the right side, they write ROM, non-volatile, read-only, permanent. And then they just stop. But Cambridge examiners are looking for the dual perspective. What are the actual similarities? Well, both are primary memory, directly accessible by the central processing unit. Both utilize semiconductor technology as opposed to magnetic or optical storage. Both are measured in bytes and organized into addressable locations that the processor can access. When you take the time to point out these foundational similarities before diving into the operational differences, you show the examiner a mature, holistic understanding of computer architecture. You aren't just reciting a list, you actually understand how the hardware works together. If you use comparative connectives and back every single claim with technical evidence, you will master the higher-order assessment objectives. Now, what exactly is a comparative connective? It's simply using words like whereas, conversely, on the other hand, and similarly. Instead of writing 2 completely separate paragraphs, one talking all about RAM and a totally isolated one talking about ROM, you need to weave them together beautifully. You write something like, whereas RAM provides temporary ultra-high-speed access for active user data, ROM permanently stores the crucial bootstrap loader. You are directly comparing them in the same breath. And then, as the ultimate finishing touch, you must draw conclusions about their relative importance to the specific scenario provided. You evaluate which one is the critical bottleneck or the most vital component for that specific use case. As you review your notes today, I want you to ask yourself this exact question and ensure every single practice answer you write from now on is linked directly to the specific scenario in front of you. Please don't be an Alex, blindly dumping facts onto the page without any analysis. And definitely don't be a Sam, rushing past those critical command words and missing all those easy method marks. I want you to be the jazz musician. Know the core concepts inside and out. Expertly apply the Peel framework. Decode those command words, and execute your answers with absolute precision. So, are you ready to improvise within a strict structure? Keep analyzing, keep the exams _IGCSE to excel in your Cambridge examinations. Subscribe right now to @acexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your exact target grade for computer science and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here.